Welcome to today's paper reading. Today's paper is titled, Anytime Continual Learning for Open Vocabulary Classification. This paper was published on AR14 by Zhen and colleagues from the University of Illinois at Urbana-Champaign. The abstract introduces the Anytime Continual Learning, AnytimeCL, approach for open vocabulary image classification. This approach aims to provide flexible prediction and update capabilities, allowing the system to predict any set of labels at any time and efficiently update when new training samples are received. The authors propose a dynamic weighting mechanism between a partially fine-tuned model and a fixed open vocabulary model to enable continual improvement. Additionally, they introduce an attention-weighted PCA compression of training features to reduce storage and computational requirements with minimal impact on model accuracy. These methods are validated through experiments that test the flexibility of learning and inference. Continual learning aims to enhance a system's performance as it continuously receives new data and labels. This is increasingly important as the scale and applications of visual learning expand. The open vocabulary setting reframes classification by comparing continuous feature and label embeddings, making it more suitable for continuous improvement. Our work focuses on anytime continual learning, where the goal is to efficiently improve the system whenever new examples are received and to maintain the ability to predict over any label set at any time. Figure 1 illustrates the Anytime Continual Learning, AnytimeCL, algorithm, which is designed to efficiently update and continuously improve with each new training example. The key innovation here is the dynamic weighting between the predictions of a partially fine-tuned model and a fixed open vocabulary model. This approach allows the system to predict over any label set while gaining expertise over time. The figure demonstrates that our method outperforms the previous state-of-the-art, SOTA, method by Zhu et al., 64, in every stage of the data incremental setting. Additionally, our method also shows superior performance in other settings such as task incremental and class incremental learning. The efficiency of our algorithm is highlighted by its ability to incorporate each new sample in milliseconds, making it highly suitable for real-time applications. Continual learning approaches can be broadly categorized into three main types: regularization techniques, which impose constraints to prevent forgetting; replay or rehearsal methods, which store and replay past data samples; and parameter isolation or expansion methods, which either fix subsets of parameters or extend the model with new parameters. Among the relevant methods, YSEFT and Paint fine-tune clip encoders and mix weights for robustness, CLCR averages model weights to balance learning and forgetting, and ZSCL uses a distillation loss to reduce forgetting. In contrast, our approach involves partial fine-tuning of clip with fixed label embeddings and a dynamically weighted combination of predictions from the tuned and original models, which allows for improvement on target tasks without sacrificing the generality of the original model. Figure 2 provides an overview of our Anytime Continual Learning, AnytimeCL, system designed for open vocabulary classification. Upon receiving a new training sample, the system completes the batch with stored samples, makes a prediction using a label embedding, and updates the tune decoder and confidence weights in one step. The new sample is then stored, and to save space and time, stored examples are encoded and compressed. During testing, the probability of each candidate label is determined by predictions from both the tuned and original decoders, weighted by their class-wise confidence weights. This method enables constant time updates from new samples while continually improving and maintaining open vocabulary performance. The green blocks in the figure represent components updated during training, while the blue blocks are not updated. The system enhances open vocabulary image classifiers by integrating a tuned model with a frozen original model. The tuned model uses the same encoder but incorporates a trainable decoder. For each image, both models produce probabilities for candidate labels, which are then weighted using online class-wise weighting. The original model in our experiments is the clip-fit model, while the tuned model updates only the last transformer block. During training, new samples are encoded and optionally compressed for storage, ensuring efficient reuse. Feature compression techniques like PCA and attention-weighted PCA are employed to improve storage and computational efficiency. The experimental setup involves three main scenarios: data incremental, class incremental, and task incremental learning. In each scenario, training samples are received sequentially, and the model is evaluated on the entire task or class set. The main experiments utilize datasets such as CIFAR 100 and SUN 397, with novel tasks including ImageNet. A total of 226,080 training samples and 1,034 classes are used. Evaluation metrics include averaging accuracy across tasks and classes, flexible inference on novel tasks, and comparisons with the previous state-of-the-art methods. Figure 3 presents a comprehensive performance comparison among CLIP plus linear, AIM, and various AnytimeCL variants across different learning scenarios. The scenarios include task incremental, A, class incremental, B, data incremental, C, and flexible inference, D, settings. In the task incremental plot, A, the online approach is illustrated by a solid line, contrasting with offline methods shown as dashed lines. The assessment of these methods is conducted at key data points, 25%, 50%, 75%, and 100% of a task's data, with tasks labeled at the 25% data point. This figure highlights the consistent performance improvements of the AnytimeCL variants over the baseline methods, particularly in scenarios requiring incremental learning and flexible inference capabilities. Figure 4 presents the ablation study results, focusing on various aspects of the model's performance. The figure is divided into several sections. A, compares different weighting methods under class incremental scenarios. B, examines weighting methods under data incremental scenarios. C, evaluates weighting methods under flexible inference scenarios. D, analyzes the impact of tuning different parts of the model under flexible inference. E, compares various sampling methods under union data incremental scenarios. And F, assesses the effect of other logit regularization under union data incremental scenarios. The results indicate that the proposed OCW, optimized class weighting, performs best across all settings and stages, especially in early stages with limited data. Additionally, fine-tuning only the last transformer block while keeping the label encoder fixed best retains predictive ability for novel labels. The study also confirms that simple sampling methods like class-balanced and uniform outperform more complex ones under a computational budget. Figure 5 illustrates the adaptability and performance enhancements of using DINO-V2 as a tuned model in comparison to the original CLIP model. In subfigures A and B, the original CLIP method is compared with the tuned DINO-V2 model using the VTB/14 checkpoint. The results show consistent performance improvements at every stage when DINO-V2 is used, particularly in later stages, indicating its effectiveness in enhancing target task performance. Subfigure B further demonstrates that this modification not only preserves zero-shot performance but also significantly boosts union plus zero-shot and mix plus zero-shot outcomes. This is attributed to DINO-V2's superior performance on target tasks. Subfigure C discusses the concept of infinite node size, indicating that regardless of the number of samples received, only one tuned model is used, emphasizing the scalability and efficiency of the approach. Table 1 presents a detailed comparison of various methods on the multitask incremental learning, MTIL, in order I, as reported by ZSCL 63. The table highlights the zero-shot performance of CLIP, which serves as a baseline. Other results are sourced from Zhu et al. 64 and ZSCL 63. The metrics used for evaluation include transfer, which assesses the model's performance on zero-shot tasks, last, which is the average accuracy across all target tasks after completing the final task, and average, which calculates the average task performance throughout all training stages. The table provides insights into how different methods perform under these metrics, offering a comprehensive view of their effectiveness in MTIL scenarios. Table 2 provides a detailed comparison of various compression methods applied to CIFAR 100 data. The table highlights the differences in memory usage, processing speed, and test accuracy among methods such as full image processing, full feature processing, VQ compression, and for instance PCA with and without CLS weighting. Notably, For instance, PCA methods show significant reductions in memory usage and processing time while maintaining high accuracy levels, demonstrating their efficiency and effectiveness in handling large datasets. The AnytimeCL approach offers several advantages, particularly in applications that require flexibility in label spaces and the ability to quickly incorporate new data without losing the benefits of older data. The approach is built on three main components: the use of complementary models to handle tasks where training data does not fully cover the label space, the ability to quickly incorporate new training examples, and the preservation of the benefits of older training data. The authors leverage techniques such as prediction weighting and partial fine-tuning to achieve these goals. Looking ahead, the authors suggest potential future work including extending the approach to tasks beyond classification, enhancing multimodal inference, and exploring scalability and federated learning opportunities. In conclusion, the proposed approach introduces dynamic class-sensitive weighting to effectively combine predictions from open vocabulary and example-based models. Additionally, partial fine-tuning with small learning rates has been found to enable a highly effective online learner. The method also includes a per-image attention-weighted PCA approach for feature compression, which offers benefits in terms of storage, computation, and privacy. Experimental results indicate that this approach shows great promise, warranting further exploration to fully understand its scope and limitations. This research is partially supported by three key funding sources: the ONR Award N00014-21-1-2705, the ONR Award N00014-23-1-2383, and the U.S. DARPA ECOL Program No #HR00112390060. It is important to note that the views and conclusions presented in this work are those of the authors and do not necessarily represent the official policies of DARPA, ONR, or the U.S. government, whether expressed or implied. Thank you for watching.